Now let's listen to Eda.
I assume everybody see my screen. So hello, everyone. So I'm going to introduce the temporal scale to track the spectral transitions in Lomas X-ray binaries. So here are my collaborators. The goal of the study is to extract the minimum time scale from a high resolution light curves for a sample of Lomas X-ray binaries. So then using that time scale to construct intensity variability diagram and compare this new diagram with the traditional hardness intensity diagram and explore how this time scale varies with fractional RMS, which is a traditional measure of variability. So we use RxC PCA data. So the sources, we analyzed 5 neutron star binaries. So 3 of them ATOLs and 2 of them Z-type and 4 black hole binaries. And we deployed a wavelet transform to the light curves to extract the MTS across the various spectral state transitions. So here you see the outburst of the sources we analyze. So we use 2 outbursts for GX3394 and 1 outburst each for other black hole source, and 2 outbursts for each of these ATOLs for U1608 and AQLX1, and 1 outburst for each Z-types and 1 ATOL. So we, to be able to extract this time scale, so we generated initially a high resolution light curves, minus 12 seconds. And then to be able to extract the fractional RMS via direct integration of the PSDs, so we used Fourier transform. So, okay, how we are extracting MTS? So we employ the Haar wavelet to represent the light curve in terms of detail coefficients. So then we are creating a log scale diagram. So in that log scale diagram, here is the white noise and this is the red noise. So this is for a high signal to noise ratio light curve. So, and then we are using a regression fit line is used to determine the intersection point. So after we extract this time scale here in Octave, so then we are converting that using to the real time scale by just using the timing of the light curve data. For the low signal to noise data, so the regression fit can not be reliable. So then we are determining 3 sigma level deviation from the noise mean to extract the MTS. So these are these different colors indicate the different levels of background noise, and these lines are indicating the minimum, maximum, and mean values. So here is our first result, which is intensity MTS diagram. This is 2010 outburst for GX3394, and this is another outburst for the same source, and this is another source. And so again, so the other 2 black holes, so we showed with 2010 outbursts of GX3394. So the GX3394 outbursts show Q-shaped tracks. And other black hole source show partial Q-shaped patterns. But, you know, I mean, when you look at the time scale, they are roughly in the same range. If you look at the neutron star binaries, intensity MTS diagram, here ATOL shows 2 distinct states well separated in MTS. Z sources clustering in a small MTS region, order of millisecond. And the ATOL time scale is relatively large, order of seconds in the high count rate state. So if you compare the hardness intensity diagram for black holes and neutron stars, so they show a similar transitional loops for black hole and ATOLs. So if you compare this time scale for black holes and neutron stars with root mean square RMS variability, a positive trend for black holes and a negative trend for neutron stars being observed. And then there is a separation with ATOLs and Z source in the small MTSs. Okay, when we combine these 2 samples, you see the black holes are in the high soft state region, which is the low MTS and the small MTS, low RMS and small MTS, and this may be related with the non-truncated accretion disk. And black holes in the low hard state exhibit a large MTS and high RMS, and this may be the case of the truncated disk. The Z types also occupy a small MTS and a low RMS region here, and atolls seems to have two distinct states, high RMS and moderate MTS here, and also the low RMS and large MTS. If we look at the hardness intensity figure, and we can identify three regions. The first region here, all sources share a common region here in R1 of the hardness and moderate MTS. And the second region, the only neutron star atolls create a separate cluster at the relatively large MTS and a moderate hardness, sorry. And the third region, as you see, black hole sources are the only occupiers of this region, which is low hardness and small MTS. That is corresponding to the high soft state for the black hole. Okay, if I sum up my talk, again, we analyze RXT observation of 9 low-mass X-ray binaries. So 5 of them neutron star binaries and 4 of them the black hole binaries. 2 of neutron star binaries are Z sources and the rest atolls. So the intensity MTS diagram for black holes is similar to the standard HID plots. The intensity MTS diagram for atoll sources is almost the mirror image of the equivalent HIDs. And the Z-type sources, form a separate cluster in the low MTS region. In the hardness MTS plane, black hole sources are the only occupiers of the very low hardness and small MTS. So this can be used as a feature to discriminate between neutron star and black hole hosts in low-mass X-ray binaries. Thank you very much. So I'm done.
Thank you, Eda. You finished very quickly, and it gives us some time to ask questions. Do we have any questions from the audience? Demosthenes, is it from the last talk? Your hand is still on, but. I think it's from the last.
Yeah, that was the last talk.
Okay. Yeah. Okay, so Hong Hui is asking, what is the physical meaning for the MTS?
So with the MTS, so we are looking at minimum time scale, which is the fluctuation right above the noise level. So and with the MTS, so you can extract a time scale which can be convertible to which we can convert to the size wherever that emission comes. So it can be, and you can, understand that which part of the disk or corona or whatever that emission is coming from by just looking the size, emission size, when you convert the time scale, direct time scale to the size.
Is there a specific energy range that you use when you calculate the MTS, or is there a dependence on energy actually?
So at the moment, we haven't checked if there's a dependence of the energy, but it should be, we assume. So we are working with the nicer data to be able to see if there's any energy dependence, but it should be dependent on the minimum energy that you use, because you are looking at the minimum structure in the light curve. The energy range we use is the full energy band of PCA. That's the specific energy band at the moment.
Okay, thank you. You have to be careful. When you're using nicer at the very, very soft energies, I think the absorption my understanding is HIDs look quite different than the RxD HIDs sometimes. So something that you need to.
But as you know, there are two absorption, right? So one is the galactic absorption and the other is intrinsic absorption. So you can subtract those two absorption by just fitting this the data, but this is going to be model dependent, and you want to keep that intrinsic absorption in calculating your HID diagrams.
You can try that right.
Do we have any other questions? Well, we have 1 minute, and I see Tom Macaroni is going to answer this question. So in 1 minute, maybe Tom can say a few words about the previous question. So thank you, Eda, for maybe Tom.
Sorry, what do you want me to answer?
Well, you said Tom Macaroni is going to answer this question live in Q&A.
Oh, sorry. I was just clicking that so that they didn't seem to be continually open questions.
Okay, I'm sorry.
Because if somebody answers it on the call, it stays open and it looks like you have, by the end of the session, it'll look like you have like 20 open questions.
Okay, I think, okay, I see, okay. So you're not going to answer those questions.
So if you just, I didn't mean to do that. Sorry.
No problem. I think they can, I think they click on it so that goes to the answer. Okay, thank you. Thank you very much, Eda, and we can actually move on to the next